Hello, teacher. My name is Dũng, and today, on behalf of my group, I would like to introduce to you to our group project. So first, let's take a look at our team member. So our team member is small, only consists of two members, so Nguyễn Thành and me, Nguyễn Ngọc. So the project we choose for the real-life application of a linear algebra is the Hill code. So here we got a table of contribution that will mostly brainstorm the idea, do the research, provide evidence, and design the PowerPoint template you're seeing right now. And for my part, I would also do the research and giving the presentation. Yeah. Okay. Let's jump right in. So here's our main content. Firstly, we'll talk about the matters needing clarification regarding the Hill code. And second, we give out example and practical application related to the Hill code. So what exactly is the Hill code or Hill cipher? So the Hill cipher was invented by Lester S. Hill in 1929. It's a classical cipher that allowed the encryption of two or three or more character in theory at the same point. Hill cipher use two other mathematical theories that are extremely important in cryptography, linear algebra, and modular digitization. It uses a variety of algorithms closely related to the subject linear algebra. So next up is the invertible matrix Z26. So if the matrix A of order MM on Z26 has invertible determinant A on Z, then the matrix A itself invertible on Z26. And that is we have determinant A equal to 0, then that A is invertible on Z, then the weighted common divisor of determinant A and 26 equal to 1. Then the matrix A is possible reversed on Z26. Since matrix A invertible over Z, there exists a matrix the inverse of the matrix A on Z96 denoted A to the power minus 1. But how do we find the inverse matrix? We can use the algebraic complement method or the Gauss-Jordan elimination method. So here a little bit of the technical definition of the Hill code. So the Hill cipher is a cipher in which P equal to C equal to Z26 to the power of M, and K is a set of matrices about the M and M that is invertible on Z26. For each matrix K belong to the capital K. So P is a set of variables come from P1, P2, etc. Pm belong to P, and C set of variables from C1, C2, etc. Cm belong to C. And it being C in the form of a definite column matrix. So the encryption function will be ek equal to k multiplied by p, and the decryption function will be dk equal to k to the power of -1 multiplied by c. If the p and c in the form of the deterministic row matrix, then the encryption function ek will equal to p multiplied by k, and the decryption function will be dk equal to c multiplied by k to the power of -1. So where k to the power -1 is invert of the matrix K on the operation performed in Z26. So here are some of the basis and the use for code information based on math and code table. So the Hill cipher encrypt M plain text character 1, so P1, P2, P3, etc. PM relate to M character in ciphertext, so C1, C2, C3, etc. CM. This substitution is done using M linear equation. C1 equal to K11 multiplied by P1 plus K12 multiple P2 plus etc. The K1M multiple PM modular 26. And it is the same for C2 and coming all the way down to CM into KM1 multiple P1 the KM2 multiple P2 etc. to KMM multiple PM modular 26. So each letter is represented by the number modulo 26. So it's not an essential feature of the cipher. This symbol scheme is often used. Here a table of encryption with 26 letter of alphabet and its assigned number. So to encrypt message, it block of n letter considered as an n component vector is multiplied by the invertible nn matrix, again modulo 26. To encrypt the message, it block is multiplied by the inverse of the matrix used for encryption. The matrix used for encryption is the cipher key, and it should be chosen randomly from the set of invertible nn matrix, modulo 26. The cipher can, of course, be adapted to the alphabet with any number of letters. All arithmetic just need to be done modulo the number of letters instead of modulo 26. Here are practice example. So we want to encrypt the plain text attack using the Hill cipher to giving a key, which is a 2-2 matrix of 2, 3, 3, 6. So since the key is a 2-2 matrix, the plain text will be converted into vector of length 2. So we got AT, TA, and CK. So the first vector, the AT assign the number of 0 and 19. The key, the original key is 2336. So we got the formula C equal to KP model 26. And some of the calculation we got the inversion called 510. So we encrypt it into F and K. Similarly with the second vector, we got M and F, and the third, likewise for the third vector, we got I and O. So all ciphertext is FK, MF, IO. And if you want to decrypt the ciphertext FK, MF, IO using the Hill cipher to a given key for our given key, we can use the formula P equal to K to the power -1 multiplied by C multiplied by 26. So the invert key of the matrix K to the power -1 will 1 over the absolute value of K to multiple by the adjoint matrix K, and would be equal to K to the power -1 multiplied by adjoint K matrix K, equal to 1 over the absolute value of D, and continue to multiple to the adjoint K matrix K equal to D to the power -1 multiplied by adjoint K matrix K. So the determinant of matrix D would be the absolute value AD minus PC, where D is different from 0. So we got D will be equal to 2 multiplied by 6 divided by 3 multiplied by 3. We got the number 3. So far the multiplicative inverse of determinant D multiplied by D to the power -1, we got 1 more 26. Using hidden trial method, 3D to the power -1, we like 1 more 26 will equal to 3 multiplied by D to the power -1 more 26 equal to 1, and we did the final result D to the power -1 equal to 9. So by the adjoint the matrix A, and we gonna apply the formula below. So we got here K, the adjoint K matrix of K will be equal to 6, 23, 10, 23, and 2. Next up, if we want to find the invert key of matrix, you can use the formula, the formula in the red, will be K to the power -1 equal to 1 over the absolute value of K multiplied by adjoint K matrix of K. So we got K to the power -1 would be the 2 matrix of 2, 25, 25, and 18. Now we describe the cipher FK, MF, and IO. We use the formula, the description formula of P equal K to the power -1 multiplied by C multiplied by 26. Do some calculation to get to the 1-2 matrix of 0 and 19 will be described into A and T. Similarly to the second vector, we got T and A, and likewise for third vector, we got the C and K. So our description text would be attack. And here we jump into the conclusion. So the Hill code is very common, easy to use, but inside it to have many shortcomings. There are 2 complex problems that using an encoding matrix. Yeah, it's not all matrices have inverse. The matrix is inverse if and only if the determinant is non-zero, and the determinant of the encoding matrix must not have any element in common with the modular space. Thus, if we calculate the modulo 36 above, the determinant must be non-zero, not divided by 2 or 13. If the determinant is 0 or has a common factor with the base model, the matrix cannot be used to its cryptographic hills and must show a different matrix. The basic Hill cipher is vulnerable to no plaintext attack because it's completely linear, blocking opponent. And to plaintext ciphertext character pair can establish the linear system that can usually be solved easily. Although matrix multiplication alone does not lead to a secure cipher, it's still a useful step when combined with other non-linear operation, because matrix multiplication can induce diffusion. For example, a properly chosen matrix can ensure that more difference before matrix multiplication will lead to a large difference after matrix multiplication. So in short, the encoding can be used to secure information in the form of short text, and then it combined with many other security methods to increase the level of protection. So that's the end of our presentation. So thank you very much for listening.